The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
So we're here today with Mikal Beau, who is the founder and CEO of CorePower. Thank you so much for coming to the office. Happy to have you here.
Pleasure to be here, Brett.
Yeah, so as we love to do on Titans of Nuclear, I would love to get to know you as an individual before we get into the work that you're doing today. So please start us off with where were you born and what was it like growing up?
Well, I'm from Norway originally, and was born in Norway, grew up in Norway until we moved to England when I was a teenager. I grew up in London, so I think of London as my home.
And why did your parents move to Norway, or move from Norway to London?
So it was my father had a job in the city, and we moved over as a family, and the family moved back, and I stayed. Went to college, started my first business, got married, had children.
Well, okay, you're racing way too fast. What did you end up studying in college?
So I studied performing arts to start with.
Okay, great.
And then I went off and did an MBA, realizing that performing arts was never going to
pay the bills.
It was going to be too much fun and too little money. So I did an MBA and then started my first company back in the mid 1990s, 96, 97.
And what was that first company?
So that was for shipping. So we started the .com for the shipping industry, the first of the .coms. That was when Yahoo was a small company. So we were really early at that stage, and it's still actually one of the few last surviving .com companies for shipping.
Amazing. Yeah. But what were some of the influences on your life leading up to that point that gave you that entrepreneurial spirit?
Well, so my father was an engineer, and my mother was a teacher, and we grew up in a time when Norway was actually, now we think of Norway as one of the richest countries in the world. But when I was little, it was one of the poorest countries in Europe.
And this is all just because of the oil boom?
All because of the oil boom.
And was your father in that type of engineering?
So he was in shipping. So he was an engineer working in shipping. And
so shipping runs through the family for you.
Absolutely, yeah, and that's what we do. In Norwegians, we're either in energy or shipping, right? That's kind of it. So I ended up working in shipping myself when I came out of college, and had my first job back in the early 90s, working for one of the big tanker organizations.
What did you do for them?
So I was selling market intelligence information on risk management, and I was quite interested in the risk management side of this business because shipping is one of those markets where everything changes all the time. The amount of risk that a shipping company faces, out at sea and in the market is nothing like pretty much any other industry out there.
And what are the big risks? Is it risk of delay of shipment, risk that the ship won't even make it there? What are the risks that are trying to most commonly be modeled in the shipping industry?
So I would say, Brett, that it's probably the most, if not one of the most, if not the most competitive and unregulated industries in the world.
Wow.
So it is a dog-eat-dog market. It's never been a team sport. It's every man to himself. And you're basically trading for cargoes that make up global trade on a daily basis. So, long-term investments in technology, and then trading the variability in the markets on top of those investments in a completely deregulated, completely global, and an entirely international market. You're competing with people from all over the world, doing with completely different standards to the ones that you might have set for yourself.
You're competing to do what? To get some good from point A to point B.
Yeah.
But then tie me back to the risks specifically that are worth being modeled in the industry. Is it just risk of commodity price changing before you get something from A to B?
So I actually came into the business, working with risk management. I spent about 30 years working risk management in shipping before I started CorePower, and it's predominantly it's a technology risk and counterparty risk market. So the investments in technology that you make are large capital expenditures, and they tend to be risks that you don't necessarily get paid for. So you go in and you spend a lot of money on investing in good quality technology and maintenance of that technology, ships and machinery, etc., even terminals, and there's always somebody out there who can do it cheaper and not necessarily better, but certainly do it cheaper. So you have this constant market risk. You have counterparty risk because the number of counterparties that you're dealing with that are not in your jurisdiction, but from somewhere else in the world.
I see. So you're talking about, when you talk about risk, you're talking about the part of shipping that is selling ships or building terminals, not necessarily getting goods from point A to point B.
No, the whole thing.
The whole thing. Okay.
Yeah, literally, it pervades the whole thing. I mean, if you look at what's happened to the American or the U.S. shipping industry, it's a shadow of its former self.
Yeah, why is that?
It's been out-competed by the rest of the world. You've got high regulatory barriers around the American shipping industry. You've got high costs that come from the way that things have been set up here, and you've got a government that's not necessarily supportive of that industry in the way that you find in other places. It's not appreciated, if you like. The value of the industry isn't so appreciated. So it's kind of lost its allure. But it's the same that's happened that happened here as it's happened in Europe. We've kind of lost that competitive advantage to Asia. It started with the Japanese, then it was the Koreans, now it's the Chinese, and then we'll see what happens next. But it's predicated on this idea that, or rather this fact, not an idea, this fact that the technology that we use today in shipping is the same as what we used 110 years ago. It's just ships are bigger, but they're the same. Nothing's. Imagine if we had cars, driving around in cars in Washington, D.C. today that were literally pretty much exactly the same as they were in the 1930s.
But, I mean, isn't that kind of the case? Up until the electric cars, we've had mostly internal combustion engine cars for 100 years. And is there anything wrong with that? Because I assume on ships, the engines keep getting better and better to run the ships too, right? So then, is there a need for innovation in ships?
Well, so what happens with this is that the competitive advantage that you get from investing in good technology, well-built ships that are well maintained, that are built to a high standard, is eroded. Because you can always find somewhere that will do it cheaper. And it's a race to zero. It's a race to the bottom. So quality becomes a secondary consideration. The environment becomes a secondary consideration. And it's extremely difficult to compete in a market where, apart from in the US shipping industry, which is regulated, which is a closed market, and outside companies can't compete here. But then it becomes smaller and smaller as time goes by.
And so what happens then? Just, I guess, different countries become good at different parts of the technology stack. Some become the ship builders, some become the ship software maintainers, some become the risk management companies. Is that how it works? And just kind of different countries, based on whatever their industries are, just take on a different part of the shipping industry?
I think what we've seen over the last 20 years is we've seen China becoming the predominant player in this. You've got a huge amount of new shipyards that are being put up. You've got very cheap labor operating under pretty appalling conditions most of the time, with cheap steel, with cheap design, sort of designed in a hurry, built in a hurry type designs, and then operated by large Chinese companies who've fed the enormous influx of commodities and goods into China. So China's been a big factor in this, but of course it started with the Japanese, then the Koreans, and then now the Chinese. Now the Japanese are starting to find themselves in a situation that, is similar to the situation that the US and Europe found itself in sort of 20 years ago, which was, the competition is getting too heavy. It's not about competing for quality, it's about competing for price. And you can always, you can continue down that route, and eventually you're going to have to, your standards are going to have to be compromised. Yeah. So I think this is the exciting thing about the shipping industry is that it is 85% of global trade. It is an incredibly vital component of everything that we do. I mean, what you wear, what you have in your house, what you come in touch with every single day has some sort of ocean transportation component in it.
Yeah, it's amazing.
The chances, cornflakes that you eat in the morning, or shoes that you wear, or, there's something in that has that part of
it's
it.
truly amazing, and I've heard the same thing said about energy, and obviously that makes sense. So let's tie these two together. When did you decide to change your focus from strictly the shipping industry to becoming part of the energy industry?
Well, so I was working as chief risk officer for a reasonably large stock-listed shipping company in New York and also in Singapore, and it was around about the sort of around about 2015, 2016 when it became quite clear that decarbonization of the shipping industry was going to become a real thing. We'd all looked at it and thought, surely not. I mean, of all things, why would you stop? Why would you stop global trade? Why would you, global trade is driven by the big diesel engine, right? It's the beating heart of global trade. Why would you stop that?
Yeah. And
you see the International Maritime Organization, which is the UN agency for maritime regulation. You see the member states, they're pushing very hard for this drive to zero in an industry that basically is the waste management stream of the global oil industry. Remember that ships burn the stuff that's left over.
Yeah, the bunker oil,
bunker fuel, that's right. The stuff that's left over at the end of the refining process. So we're sort of, waste to energy, right? But it's happening, and it's being pushed harder and harder and harder, and these limits are being set for 2030, 40 and 50, where the industry has said, well, you got to go to zero. Well, these ships, Brett, are huge.
Yeah.
I mean, talking about 400-meter long ships that, carry hundreds of thousands of tons of cargo.
Yeah, it's amazing.
It's very difficult to imagine how you were not going to run an efficient energy system on board those.
Can I ask a silly question before we get to the solution that I think everyone knows that we're getting to? Let me just ask a silly question first. The shipping industry used to be powered totally renewable, right, through wind, right? That was the original ship propulsion technology with sails. How come that never evolved to just make like giant sails or some other type of like wind? I mean, there's plenty of wind out in the ocean, right? So how come, or like directed wind funnel energy? I mean, how come that science never advanced? Because you figure, they got a lot of wind out there, and it started off that way, that someone would invent some sort of new sail technology.
Well, look, there's no such thing as a silly question, is there? But to be fair, until steamships and the big diesel engine came along, we didn't have globalization. You had some international trade on small wooden ships.
Yeah.
I mean, you look at the biggest sailing ships in the world as they were in the 1870s, and they're smaller than yachts these days, right?
Yeah.
So you'd move a few hundred, maybe a few thousand tons of cargo around very slowly, and you'd have to sit and wait for the wind to turn in order to be able to leave the harbour.
Yeah.
Now, with the dawn of the steam engine and the diesel engine came after that, you then had this opportunity to keep goods moving.
Yep.
And you could then start, properly exporting from one country to the other. Countries that were exporting raw materials to places where you'd started adding value to them. Steel industry started to come through, the Industrial Revolution. You started seeing a lot of movement of coal for energy. I mean, we were digging coal in our own backyard before then. Now we can start importing it. We had grain transportation. You had the transportation of durable consumer goods as the container shipping industry started coming through in the 1970s. So, it enabled a huge amount of innovation, and it gave us globalization. If we stopped that, you'd have to say, right, globalization is over.
Yeah.
Small wooden ships that bob on the top of the sea with big sails, fine. But if we've got a 400,000 ton ship carrying iron ore from one part of the planet to another, no matter how much wind you put,
it's all about size and weight. Okay, great. So then you probably need something a little bit more power dense. That's what brought us to fuels, and now to the next generation. To tell us about that. Tell us about how nuclear gets applied to the shipping industry now.
So there's two sides to this, and what we were talking about earlier on was just this idea that as the industry's sort of competitiveness drives the costs, there's a race to zero, it becomes very difficult to be competitive. So we need to find a new way to be competitive, and that comes from innovation. That comes from a new way of doing things. It's the same as when we went from sail to steam and from steam to diesel. Something else has to happen. And this has been driven by this global community's wish to go to zero. So if you're going to have zero emission vessels, well, you're going to have to abandon combustion. if you're going to abandon combustion, what have you got left? What can you do? There has to be a nuclear component in it. So I think the way we see it, Brett, is, you know, we don't see 100,000 ships out there with the reactors on board. Certainly not. For propulsion, I don't think that's really the way that this is going to go. I think we're going to see a sort of bifurcation. You know, the very largest ships out there could benefit enormously from nuclear propulsion.
How many cargo ships are out there in the world?
About 100,000.
100,000 that do like what I would think of, like shipping containers.
Yeah, and bulk cargoes. So dry bulk
great.
cargoes, liquid bulk cargoes, and then break bulk, you know, so things like cars and trucks, etc., and then you have containers.
And what is the history of nuclear power in the shipping industry? Because there have been prototypes, experiments, full ships that have done this before. Tell me about that.
Well, you know, so all the reactors operating in the world, or have operated in the world today, you know, more than half of them have been at sea.
Yeah, like submarines.
Submarines, you know, naval vessels. But it's a very different thing. You know, we can't use naval technology in civilian shipping. It's inappropriate. It just doesn't. It's not fit for purpose. It's good for the Navy, but it's not good for the civilian industry. And the examples we've seen of commercial vessels or demonstration vessels. There was one here in the U.S. back in the 1950s and 60s called the Savannah. She's moored in Baltimore. She's a beautiful ship, the Atoms for Peace ship. But she was a demonstration of you know what nuclear could do as a civilian industry rather than as a weapons industry. And you know, in order to move this reactor around the world and show it to people, they had to put it on a ship. So they created this beautiful ship and moved it around. But she wasn't really a commercial ship. She wasn't meant to make money.
But how come it didn't catch on then? If obviously the technology works at sea, the submarines have it, and they had the idea back then. What stopped it from maturing?
So I think what's happened is that we've only really had access to, or we've only really had one technology that we could conceive of using at sea, which is the pressurized live water reactors, pressurized water reactors, naval reactors, effectively, and there's a massive barrier. There's a regulatory and legislative barrier to the civilian industries, commercial shipping industry using naval reactor technology because it's the domain of the Navy, and that quite rightly so. They don't want to share that with anybody. They run on high enriched uranium, right? Very high.
The naval ships, the naval submarines used high enriched uranium, right? Okay, so that's out.
So that's totally off. So now you're going to use low enriched uranium in these reactors, which is perfectly feasible. But then you've got a refueling cycle, which is every 18 to 24 months.
And what's wrong with that?
So by extension, what you would have is you'd have vessels having to be refueled either at a lot of refueling stations around the world that the infrastructure would have to be built out for, or you'd have to do imports. And now you've got non-proliferation, and you've got security issues and all these sort of things with refueling a reactor in a commercial port. The second thing, which I think is key, is that all of these pressurized reactor systems require an emergency planning zone around them that are, by extension, quite large.
And so why is that different for non-pressurized reactors? Because
in a non-pressurized reactor, you have in theory at least, you have the possibility of shrinking that EPZ down to the boundary of the vessel. If you've got a low source term and you've got an ambient pressure reactor, you could then contain that reactor on board a vessel and not have the EPZ extend beyond the boundary, and that changes the liability regime around this.
I'm not quite following the logic there. What does that have to do with pressurized technology? To me, my understanding is, irrespective of how you split the atom, you are left with a certain amount of radioactive material, the actinides or fission products. That's every single technology. So you have the source term there, and then the emergency planning zone, as far as I understand it, is about, in an emergency, the movement of that source term.
That's right.
And so there are different types of emergencies that might get created. Some of them might have to do with the pressure, but most of them, as far as I understand from a licensing perspective, don't have to do with pressure. It's a matter of, what if someone attacks your equipment? Whether you are a high pressure system or a low pressure system, you have a collection of radionuclides, and the thing that may attack your system could spread that same source term out an equal distance, whether or not it was a pressurized reactor versus a non-pressurized reactor?
So with pressurized reactors, of course, you have the potential for the formation of a plume. So if you have water-cooled reactors with high-pressure steam inside, you have that potential formation of a plume. Now you can contain that, but the rules and regulations as they are today set that emergency planning zone at a certain size around it.
But why would another technology not have a plume?
If you have a non-pressurized reactor and you have no formation of any hydrogen from water that's cooling that reactor or any high pressurized gas that's in there, then even if you have a leak, you will not have a plume that would come from that system.
Maybe we'll come back to that because I do want to hear a little more about your technology. So tell us what your solution is.
So we've been working with literally looking across the whole spectrum of different types of technologies that are out there and seeing which ones are the ones that can meet these key criteria for maritime. And the key criteria for us to be able to use this in maritime, and we're talking propulsion now, which of course has other challenges too, and not least export control, but also for use in floating nuclear that you can use to create synthetic fuels for the industry and off ports around the world. The three criteria that we've identified together with the industry that need to be met in order for this to succeed is that we need, first of all, to be able to create a system that has an emergency planning zone that is small enough to us to be able to shrink the liability around moving these reactors in and out of ports and moving up and down waterways. Because an emergency planning zone that extends into a port or a port city, it's basically an unlimited public liability that no commercial civilian shipping company would be able to or even be allowed to take on. So this is why it's naval technology for the most part. It has a nation standing behind it, and that's the guarantee. The second one is that we have to be able to make these reactors affordable. So we have to go from that. I think like so many people who've come on this podcast before have probably said, you need to go from a sort of project to a product. We need to be able to manufacture these reactors in a way. So you have to have the manufacturability, the modularity and the manufacturability. I think you guys are working on this too, to be able to do this. And it has to be small enough then to be able to fit and give the right kind of power. And the last thing is, I would like to see us running very long fuel cycles. So the idea that we don't have to stop reactors and refuel them in ports around the world, but rather have reactors that could function for a very long time without refueling, potentially with inline refueling, so that you're topping up at full power rather than stopping and taking and replacing the fuel, gives that potential for a sort of upfront capex on the energy system that lasts for the lifetime of a ship, which is usually between 20 and 30 years. Okay, and so this led you to which technology? So then we looked through pretty much everything that's out there, and we came down to the conclusion that the two ones that really meet these criteria, there are others that could potentially meet this as well, but the ones that meet them the best is the molten salt reactor. And of course there are different types of molten salt reactor designs out there as well. And the second one is the heat pipe, micro heat pipe reactor, which we think is a very interesting potential to do this. It's sort of more like a sort of battery type thing rather than just a reactor. The molten salt reactor is one that we thought was or we still think is probably the one that has the ultimate solution for this. But in looking at then who's developing molten salt reactors, who's looking at different types of designs and what they're doing, you get down to that second set of criteria that we haven't talked about, but which I'll bring up now. And that second set of criteria is really, if you're going to do this, the most important thing is that there is a feasibility in execution. Can they actually be built? Are the guys that are building these things, do they have the facilities? Do they have the people? Do they have the skills? And do they have that awesome financial firepower behind them that you need in order to get to a point where you can not just demonstrate, but commercialize this technology? And I think that's that's the big issue for Gen 4 reactors today. Is it's getting the investments in behind the technology, which is driven by a customer base that actually has demand and offtake possibilities for this technology, and getting them interested and excited in this on the basis that they can see quite clearly that yes, the team that's building this has the capability, and they have the support and the financial firepower to be able to actually do it. Because I think all of these reactors will work. I mean, somehow they will all function if you built them, but which ones are actually going to get built? So we've chosen then to work with certain select parties, and we're very pleased with the way things are going.
So which select parties meet that criteria?
So we're on a team with TerraPower and Southern Company to develop the molten chloride fast reactor, and then we've chosen that for two reasons. One is that the molten chloride fast reactor, which no one's ever built before, so it's it's a technology risk right there. But the fact that it's a molten salt reactor without a moderator, which tends to be a graphite moderator, enables us to avoid that issue of exchanging that moderator every 6-7 years. Again, a big issue for the reliability and the sort of maintainability of a marine system. So if we can get the molten chloride fast reactor to function properly, and we can get it to work as a long-term reliable machine, then it is potentially the ultimate solution for the shipping industry.
And so you said you started to work with TerraPower. So what's the division of responsibilities between your company and their company?
So it's a team effort. So we operate under this risk reduction award that was issued by the Department of Energy under the Advanced Reactor Demonstration Program. And the risk reduction award is really there to eliminate some of the key risks that sit in developing this type of technology, corrosion and erosion, or thermal hydraulics, etc., which we need to be done. I mean, there's still a long way to go. Now, there's three companies in this group. It's TerraPower, it's Southern Company, and it's CorePower, and we all bring something to the table. And TerraPower, of course, are the reactor designers and the builders of this technology and phenomenal capability. Southern Company are the ones that have the nuclear operating experience, that bring the licensing and regulatory side of it, as well as the operational side of it. And we're bringing, if you like, the market. We're bringing the customer demand for this, and bringing that manufacturability, the capability and manufacturability of these systems for a larger market. And that focus is not on propulsion. That focus is then on floating nuclear. So if we can demonstrate that we can make these reactors work in a marine environment, which is a dynamic environment, it's pitching, it's rolling, not to an extent, then we're creating a reactor system that would also be perfectly happy on land. So if it works at sea, it works on land, but not necessarily the other way around. So if we can demonstrate this as a floating reactor system, where you're basically taking the idea that you're manufacturing reactors in an environment either in or near to a shipyard that is specifically set out to build floating nuclear power stations, we could create a manufactured floating nuclear power station product that, instead of having a workforce of thousands of people that are moving from project site to project site, they're now staying in the same place and building the same machines all over, again and again. So we can then float them out to where they need them. They can sit on the coast.
So is that what you guys do? You take the core technology that TerraPower is building for their land machines, and you're adapting it, and are you custom designing a ship that goes around it as well?
So we're custom designing the floating nuclear power stations around that. So we're not focusing on the ships. That's something that could come later on. Remember, we have something called the International Trade in Arms Regulation, ITAR. That sits here in the United States, part of the U.S. munitions list, where naval nuclear propulsion is an item, and it's not an exportable product at this point. So ITAR stands in the way of us being able to promote this as a propulsion product, unless, of course, it's entirely a U.S. fleet operating in U.S. waters, which is perfectly possible, and we could potentially get to that. But at this point, we're focusing then on getting these reactors out on floating power. So you have, if you like, mobile power stations that you can manufacture in one place and then move to a static place or a site where they would sit, feeding coastal industry, feeding power to floating systems that would desalinate water and create green hydrogen and synthetic fuels, etc. That would either feed land-based transportation or ocean transportation, or they could be used as part of an energy system where you're load following for offshore wind, for example, in front of a land-based energy system.
But I guess maybe I'm still having trouble understanding what exactly is your product. What does it look like? It's a power plant wrapped around TerraPower's core that goes on a ship?
We think of it more like in a modular fashion. So the power plant itself, the power station itself. I wish I could show you here, but we have several designs. One of them is what's called a spar design. So it's a circular hull with a skirt underneath it that is very, very stable hydrostatically, and it's perfect for places like the U.S. Gulf and the Atlantic and other places. It's used in the offshore oil and gas industry a lot. And it is a phenomenally stable and large scale sort of steel structure. And we're then looking at how we could then fit the reactors themselves, then pre-manufactured into these in a modular fashion. So in a sense, they're manufactured separately. So we're not building the power station around the reactor, but rather building that power station, that floating power station, with all of its power conversion systems, its turbine technology, and its electrical systems, and then having the reactors then fitted to that. But in these specialized shipyards, that we're looking to establish.
But does TerraPower have to redesign their core technology to fit in your application? How big is their standard power block? How much power does it create?
So it's still early stage, right? So we're still in the risk reduction awards part of this. So that's still to be determined. But we could get this up to, I think the standard large design version of this machine would be 720 megawatt thermal.
Okay, so you're going to build, and so that's your concept. Then you're going to take their 720 megawatt thermal reactor core, and then you are going to build something around that to create power on the ocean.
Yeah.
Okay, and then that's your part of the product, is you build that system that integrates into their standard core. But they've got to get it to you somehow, right? So they're shipping. Where are they producing their core?
So the concept here, Brett, is that we would produce these two in the same place.
Okay, so you're teaming up with TerraPower to create a new manufacturing facility that is going to make both their core and also your balance of plant, for lack of a better term, that goes around it, that is an ocean-worthy structure. And then you're going to drag it, float it, move it to whatever your customer is.
That's the concept.
And when? Give me the when and how much question that everyone always wants to know. So when would the first one be built and operational, and how much is it going to cost?
Difficult to answer both of those questions, actually, because we don't know. But I'd say that the earliest that we could possibly do this is in the mid-2030s. We need to be able to demonstrate that the technology works. We need to be able to demonstrate that it works, in a floating environment. We need to be able to demonstrate to the licensing authorities that this is the right kind of approach to this, and that they would be happier for us to do this. That's not a trivial matter. Mm-hmm. And then if we can start demonstrating this in the early to mid 30s, not at a full commercial scale, but in a small scale system, I think we can start getting these out there sometime in the 2030s. I mean, if we have a full scale one out by 2040, I'd be very pleased. How much is it going to cost? That's a lot of that is guesswork at this point. But we've looked, rather than the actual costs of everything, we've looked at the comparative costs between building a similar sized power station on land in the way that you would do with large construction project, lots of concrete, lots of people, etc. We've looked at the efficiencies of doing this in the shipyards, and we've got a number of large shipyards as our shareholders, and help us with understanding what their various processes are, etc. And we've looked at all of the various component processing in creating these power stations, the same way that you would do ships. You don't build one and then you start on the other. You start with one, you move that portion to the next part of the shipyard, then you start again with that. So you're constantly building. So you could potentially build 9 at the same time, but slightly just behind each other. So I think we can get the cost of construction down to less than 50% of what the standard cost is today. And we can get the time of construction down substantially as well. But that's still guesswork.
2040 for the first commercial scale one seems pretty far out, and that seems like a pretty high price to pay for the technology decisions that you've made, about the potential plume or whatever it was, or the long fueling cycle. Why not build something that could be built in just 3 or 4 years and just get something up and running and sacrifice maybe some of your original criteria? Not have it last 20 years, but have it refuel every 2 years. I mean, normal plants refuel every 2 weeks. So, why not lean up on some of your initial criteria just to get a product out the door faster?
Well, I mean, that's the beauty of doing it this way. I mean, we're all contributing towards, if you like, a sort of an ultimate solution, we think, for a sustainable energy system. But each one of these components can be used in many different ways. So that floating power plant that we're designing is not designed specifically for this technology, but it's designed with that technology in mind. So you could potentially put a BWR or a high temperature gas reactor or whatever you wanted on this. I mean, that's really up to the operators.
But why not make that the original plant? Since your company's primary IP is not the reactor core, and you've got a business to run, right? And you've got this grand vision about decarbonizing global transportation energy, which I love. I think that's just an amazing vision to work towards. So kudos to you and your team. But why not just take whatever the most off-the-shelf reactors right now, whatever the Russians are doing with their icebreakers, the KLT 40S or whatever it is, why not just start with that? Get them to build you, or not the Russians, but someone who can build whatever they built for the KLT, hire Westinghouse, hire GE, hire Babcock and Wilcox, BWXT, sorry. Hire someone who can just make you the simplest, hire the Argentinians who have an SMR, and then just put that on some sort of metal skirt platform that you're talking about and just get something going, get the first 10, up and running in the next 3 or 4 years, and just put them in not every application, but an application that works.
That could well happen, Brett. That could well happen. Look, I think we have to approach the way that we build a business in this area. No one's ever done this before, right? Mm-hmm. So we have to approach the way we build a business in this, taking pretty much everything into account. And I've got a fondness for working backwards. Now, our ultimate aim here is, if we can do this, is that we can get reactors out as propulsion units on large ships. So you go back to the propulsion part of this. Out of those 100,000 ships that we're talking about 7,000 of them consume 50% of all the fuels in the world. So you're not talking about that many. It's not that large portion of the fleet that would basically cut emissions in half and substantially change the competitiveness of our industry. I think if we work, in a sort of one step forward at the time in whatever is the easiest way, whatever the easiest win is for each step that we take, and we move forward in that way, we'll end up going down routes and avenues that are not going to get us to the target. I like to think of the big prize here, which is that new, exciting, never done before technology solving these massive problems that we have in our shipping industry and in lots of other industries as well, and then rather think backwards from that. So if we then, through those steps, start going forwards again and say, well, what can we do with each one of these component parts? Small power stations that are built in shipyards, large power stations, medium power stations, whatever other floating concepts that are there, can be used for different technologies, with different vendors, with different jurisdictions, etc. And absolutely. But I think the way to get there is not to pick one and then go for it, because you end up going down this cul-de-sac of developing that system, and that's it. That's how this industry tends to work. You find a solution, you go for it, that's it. That's the direction you're going. We've got our eyes on the big prize here, which could be a very long term. It could be something that we achieve long after I've gone.
You said it out loud first, not me. But doesn't that scare investors? Doesn't that scare employees? How do you create the momentum to sustain your company and raise the capital when the first product is going to be almost 20 years, the first commercial product will be almost 20 years from now? I guess that's once again, I can't tell you how happy I am there are people like you in the world that are trying to like take bite off these like huge projects and really just important problems. But it just makes me so nervous anytime someone in the nuclear industry is willing to wait 10 years to see their product come to market, because to me 10 years might as well be never, because yes, you might be trading off some risks, but you're taking on just like the everyday capitalization of your company risks and motivation of the employees risks. How do you deal with that?
So it's interesting, because when you think of investors in companies like ours and yours and other companies out there, you tend to think of venture capitalists, and you tend to think of the sort of professional investors that are looking for a short-term return. We have never spoken to a venture capital firm. We don't have any venture capital investors in our company. Our company is invested in by those that effectively will form the order book in the future. So this is the shipping industry. Mm-hmm. We've got large household names from the shipping industry, shipbuilding industry, big industrial corporations that make their living off the shipping industry, investing in us because they have a different outlook on these things. They don't think about the return over the next 3, 4, 5 years. They think in terms of, they obviously do, but in terms of when they're investing in us, they think about the next step beyond that. I mean, let me give you an example. So the vast majority of all shipping companies in the world are family-owned companies, and they pass from generation to generation in an extremely slow manner. Some person started this company 100 years ago. It's been passed to the son or the daughter, and it's going to continue happening for generations. And when the handover happens, it comes with a brief job description, and that job description has just 2 items on it. And the first one is, don't lose the money, and the second one is, make sure that by the time it's your turn to hand over the reins of this empire, that we're future ready. So make sure that you've gotten into the emerging technologies and emerging markets that we need to be able to be in, so that in 20, 30, 40 years time, when this company passes over to the next generation, we can do this. That long-term thinking, that extreme conservatism that so many people are afraid of, is actually a fantastic benefit to firms like us, because we've got these billionaire families that are saying, look, we understand this is going to be the solution, because what else is it going to be? Is somebody going to come up with some magic thing that's going to drive this forward? Global transportation, ocean transportation, global trade, it's not going to go away. It's going to continue to grow, and it's going to be an extremely important part of the global economy. And these guys are the guys who serve it. So I think that's we've approached that differently, and that works really well. I mean, we've just literally closed the third round of funding now, which will took record amount of time, and record short amount of time, I should say. Sorry, and we brought in some unbelievably large cap companies into our company.
And how much did you raise, and how much do you need to raise?
We raised 100 million.
We raised 100 million
in this last round. Great.
And what does that 100 million get you to? What's the next milestone?
So that, I think, gets us to the back end of this molten chloride reactor experiment that we're in the DOE program with TerraPower and Southern Company. It enables us to stand up to all of the obligations that we have to fund our part of that, and to continue to expand our system around it. I mean, obviously the studies on manufacturability, the investments in the kind of teams and engineering capabilities that we need to be able to create these designs, to bring these designs forward, to start doing testing on some of these designs, start doing some of that maritime regulatory work that's required to do this. That's all fed by this. It's certainly not the end of it, but I'm very confident, having been able to do this. We're a 4-year-old company, Brad. And we've gone from what was effectively a crazy idea on an airplane to where we are today, and we just raised $100 million, and I think we can continue to do that, because the spread of the investors in this round, it's not like somebody has come in and put in 90 of that 100. I mean, there's a lot of big companies who've come in and taken a chunk of it, with the idea that they would come in and follow that money and support us as we reach milestones, as we develop this business.
And so tell me just a little bit more, with a little bit more granularity, that $100 million. What are you conducting physical experiments? Are you funding licensing exercises? How do you spend that money moving forward? So headcount, where does it all go?
Very large part of course, goes into our cost share of the reactor development program. Right?
And break that out for me. So you put money into this consortium with TerraPower and Southern, and you own some part of the IP that comes out of it. Is that the idea?
So the idea is that we share the ownership of the technology once it's built and
so you have a perpetual license to use it.
Yeah.
Can you also relicense that technology?
No, we would be a partner in the joint venture that would sit around this technology, and that joint venture would be responsible for licensing. So we would probably be
that joint venture owns IP as well. It's not just a project entity to build something.
Correct.
Okay, great.
So a large portion of the money goes into our portion of the cost share and developing that technology, and then then there's sort of two big parts that come on the outside of that, which is really on the marine side. One of them is that engineering and designing that we do. We have an in-house naval architecture studio that works with the shipyards that we have as shareholders and others, to develop the designs of various floating solutions, from very small to very large and everything in between, and all of the component parts of that. Then there's a lot of engineering that goes in behind that. A lot of that's engineering design, a lot of it's testing, a lot of it's the kind of things that we do at this early stage. We haven't built anything yet that floats. And then the second part of it is really the regulatory side, because licensing and regulation on the nuclear side, of course, we leave to the team. I mean, we've got Southern Company on our team. They're, I can't think of anyone who's better at doing that, and we certainly wouldn't want to get involved in that process with NRC, etc. But on the maritime side, we've got the US as a flag state, we've got the UK as a flag state, we've got Japan as a flag state. These are all members of the International Maritime Organization. And at the International Atomic Energy Agency in Vienna, there's collaboration between the IAEA and the IMO on what happens in the floating domain. There's many people talking about floating, but we're actually building designing solutions for this. So making sure that we can support those the agencies of those member states to be able to drive the right kind of rule changes and modernization of existing rules. I mean, there are rules that have been in place since the 1970s for floating, but they're kind of old. They're a little out of date now. They don't really reference all the latest rules and regulations from the IAEA and the IMO and anywhere else for that matter. So we support them. We work through NGOs here and in Europe to make sure that we can support all the right kind of documentation, data, and everything else that goes behind making sure that we have appropriate rules by the time we get to build these. And my hope and aspiration is that new appropriate versions of these old rules are available for scrutiny at the IMO already in 24, 25.
And tell me more about the nuclear licensing component. I know that's not going to be your domain, but do you have some estimate as to when that'll be complete, so then you can start informing the rest of your business growth?
No, not at this point.
Okay. Before the end of the decade, or not until the 2030s, do we think we'll have a nuclear license on that core part?
We'd like to hope that this is this is a process that's already started. It's a process that, every regulator that you go and speak to say, please come to us first. Come to us at the beginning. Come and talk to us from the start so we can understand what it is that you're doing, rather than come towards the end and say, look, this is what we built. Can you take a look at it? So I think, that long-term process with the primary regulator, which is likely to be here in the United States, is something that's discussions have been going on for some time, and they will continue to evolve into what is effectively a licensing process, but we're not there yet.
Okay, great. What else should we know about your business?
We are a 4-year-old business, and we have set up here in Washington, D.C., so we're growing our presence in the American market. We have a small office here run by our trusted colleague, Tony Houston, who's actually sitting in the room with us. And we're building our team here. as we speak. We're going to be opening an office in Tokyo in the summer, probably in June. We'll see, but it's going to be May or June. And those are the three sort of centers that we're going to be working in. So we have a business that's split across marine engineering, naval architecture, regulation, client programs. Not only are we building technology for this market, but we're also building a market for the technology. This demand from the global shipping industry and ocean transportation is not one that is identified easily. So we've been building, specifically a client program for shipping companies and industrial companies and energy companies to come in and be part of this process. And it's going extremely well.
Great.
Yeah.
And any final words for our audience?
Merry Christmas.
Merry Christmas and a Happy New Year. Awesome. Well, thank you so much for coming in, telling us about your very exciting company. And where can people go to find more information? Do you have a website or a URL we should share?
CorePower.energy.
CorePower.energy.
So yeah, come and talk to us.
Awesome.
We're always happy to have discussions with anyone.
Thank you.
Yeah, lovely. Thanks very much, Beau.
Great.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.